Okay, so we've spent a lot of time on the theory behind support vector machines. But how do you actually use one in a real project? Let's forget the dense math for a minute and get right into the practical steps you need to take to get awesome results. First things first, let's just get a common fear out of the way right now. You might be thinking, oh no, do I have to code that crazy complex optimization algorithm from scratch? And the answer, thank goodness, is absolutely not. Seriously. It's like writing your own code to calculate a square root. You just wouldn't do it, right? You'd use a library. It's the exact same idea with SVMs. So you can breathe a sigh of relief. Your job is not to be some numerical optimization genius. There are already super optimized software packages for that. Your job is to be the pilot, the strategist who makes a couple of really key decisions to tell that powerful engine where to go. And that really brings us to the main idea for this whole explainer. The pro's secret to using an SVM isn't about being a master coder, it's about being a smart chooser. It's all about making the right choices. And you know what? It really just boils down to two main decisions. That's it. First, you've got to set that regularization parameter, which we call C. This is basically you telling the SVM how much it should sweat the small stuff, how much to worry about misclassifying any single data point. And second, and this is the big one, you have to choose your kernel function. This is what's going to define the entire shape of your decision boundary. Now, both of those decisions matter, for sure. But your choice of kernel, that is, without a doubt, the most important, most fundamental choice you are going to make. So let's really dig into that, because this is what unleashes the true power of an SVM. So what the heck is a kernel, anyway? Well, the simplest way to think about it is as a similarity function. It's a little machine that takes two of your data points, looks at them, and spits out a single number that says, hey, these two are this similar. And this incredibly clever trick is what lets the SVM go from drawing boring straight lines to creating these beautiful, complex, curvy boundaries that can separate even the messiest data you can imagine. Now, if you start digging around online, you're going to hear about all sorts of kernels. Polynomial kernels, string kernels, all this other fancy stuff. But here's the reality check. 99% of the time, your choice is going to come down to just two, the linear kernel and the Gaussian kernel. These are the workhorses, the ones you'll actually use, so let's just focus on them. And to make this choice super clear, let's just put them right next to each other. A good old-fashioned head-to-head, so you know exactly when to reach for one versus the other. Okay, the guidance here is actually pretty straightforward. You're going to want to use a linear kernel, which, by the way, is kind of like the no special kernel option, when you have a ton of features, but maybe not so many examples. Think about classifying text, right? You could have thousands of features, one for each word, but only 1,000 or so emails. A simple straight line is probably your best bet there to avoid overfitting. But on the flip side, you use the super powerful Gaussian kernel when you have fewer features but a good amount of data. This is where you really want to fit a much more complex, nonlinear boundary. All right, you've made your big choice, you've picked your kernel. Awesome. Now let's cover a couple of absolutely essential pro tips that you've got to know to make sure you're getting the best performance possible. This is especially true if you went with that more powerful Gaussian kernel. So let me ask you this. We just said the Gaussian kernel is all about measuring similarity, right? Which is really just about the distance between points in space. So, keeping that in mind, why do you think scaling your features is an absolutely critical, non-negotiable step? Well, this chart just says it all. Imagine you're working with housing data. You've got one feature, house size, which is in the thousands of square feet. And then you have another feature, number of bedrooms, which is like 1 to 5. When the SVM goes to calculate the distance between two houses, the gigantic numbers from the house size are just going to scream over everything else. The bedroom count, which is a super important feature, is barely a whisper. It gets almost completely ignored. But look what happens after you do feature scaling. We put both features on a similar scale, maybe something between 0 and 1, and suddenly it's a level playing field. Both features can now contribute fairly to that distance calculation. The SVM can give a comparable amount of attention to all your features, and that, my friends, is how you get a much better model. And one last quick pro tip. Whatever you do, please resist the urge to get creative and invent your own kernel. It turns out there's a good reason we stick to the ones that already exist. For all that fast, optimized software to actually work, a kernel has to satisfy a pretty technical math condition called Mercer's theorem. So we stick to things like linear and Gaussian because they're guaranteed to play nice with all the optimization magic happening under the hood. All right, let's zoom out. You now have the tools to actually use an SVM. But the bigger question is, when should you pick it over something else, like logistic regression or even a neural network?
Let's put together a quick and dirty cheat sheet.
This table is basically your go-to guide. Let's say n is your number of features, and m is your number of data points. If n is really big, but m is pretty small, stick with logistic regression or an SVM with a linear kernel. Now, if n is small and m is kind of an intermediate size, maybe up to 50,000 examples or so, an SVM with a Gaussian kernel is often a killer choice. But if n is small and m gets huge, that Gaussian kernel can start to slow down. In that case, you're often better off creating more features yourself and then just using a simple logistic regression or a linear SVM.
So where do neural networks fit into all this? Well, the truth is, a really well-designed neural net can work well in pretty much all of these situations. The biggest trade-off is usually that they can be a lot slower to train. One huge advantage for SVMs, though, is that their math problem is what we call convex. What that means for you is that you don't have to worry about getting stuck in a local optima. Finding a pretty good answer but not the best answer. An SVM will always find the single best solution, which is one less headache to worry about. And that really leaves us with one final thought. After all of this, is picking the best or fanciest algorithm really the most important thing you do in machine learning? What the experts will tell you is that often what matters way more is how much data you can get and how good you are at the other stuff, debugging, analyzing your errors, and coming up with smart features. The algorithm is an incredibly powerful tool, for sure, but it's still just one tool in a much bigger toolbox.